the next thing that we want to look at is the definition of what do we mean by a convex function, right. So, we have seen what are convex sets, now we need to understand what are convex functions, and because we want to eventually in machine learning think of the goodness of whatever that we are outputting, and the goodness will often be measured using some kind of a performance function, and more often than not in machine learning we will encounter functions which are of convex nature for a particular reason that we will see in this course in by the end of this lecture. But before that we need to understand what do we even mean by saying that a function is a convex function. Now, there are several alternate definitions for thinking about a function as a convex function. We will see couple of these definitions, and it's important to understand all these definitions because it gives you more complete perspective of what convex functions are, right, and how to recognize a function as convex. If tomorrow you have to prove a function is a convex function, it would be good to have in your armor all possible ways of attacking the problem. Right. So, that is why we will give multiple definitions of convex functions. Okay. So, the one of the easiest way or one of the ways that will easily build from whatever we have already seen, which is the notion of convex sets, is by understanding the following definition, right. So, we will think of a function of in general as RD to R, any function that takes d inputs and then spits out a real number, but it is always easy to visualize this in 2 dimension or 1 dimension, in this case R to R functions, right. So, think of this as x and this is f of x, and we somehow want to argue that maybe this function is convex or not function or not convex. So, we need to kind of give a definition for what do we mean by a convex function. We know what are convex sets, we need to define convex functions, right. So, we are going to think of it as RD, but in general you can also think of this can be any convex set, right. So, maybe you are looking at a function which is restricted to a particular domain, and that domain has to be a convex set, right. So, your function's value on that domain, now you can ask whether your function is a convex function or not. If the domain itself is not convex, then the function is not by definition a convex function, right. And if it is RD, then naturally this is a convex set, and so that problem of thinking about whether the domain is convex or not does not arise in this case. But okay, so but there are several functions from RD to R, not all of them are convex. We still have to define what do we mean by saying a function is convex. Here is one way to define this. Now, we are going to define, given a function, you give me a function f, I am going to define a set out of this function, right. So, because I only understand convexity of sets at this point, so I want to understand, I want to give a definition of a convex function via the notion of convex sets that we have already understood. And so, given a function, I am going to define a set out of this, and that set is what I will call as an epigraph, in short AP, is just a set, right. So, think of this as a subset of RD. In fact, this we will see it is not a subset of RD, it will be RD plus 1, but let me define this. Okay. So, what is an epigraph? An epigraph is the set of all points of the form x and z, right. So, it is a point in d plus 1 dimension, right. So, this is in R d plus 1. Now, what is so special about this x and z? Well, you should have somehow you have to relate it to f, right. So, because this is a set that is associated with f, and the way we will associate with it is by saying that we will consider all those points x comma z where z is greater than or equal to f of x. What do I mean by this, right? So, this means that if I am given a function like this, now I take any x and I want to look at which are the points that I am considering in the epigraph of f. Well, it is going to be the set of points. Now, I should think of this as a 2-dimensional plane where I will go x in this direction and in the the vertical direction, I have to go at least f of x, right. So, anything above or equal to f of x is okay. So, which means that this would be f of x. So, this point would be in my epigraph, not just this point, this whole line, right. So, this is not going to be there, right. So, this was just to show that this is at f of x, right. So, this is x1, let us say f of x1, right. So, now all these points, this is like an infinitely extending line, but yeah. So, this is nevertheless this line, right. So, now I do this for every point, which means that the set that I am associating with this function is this set, right. So, now this is the epigraph of f. It is a set in Rd plus 1 because your x itself is in Rd and the value that x takes is f of x, which is a number. So, you add that extra dimension, right. So, the definition now then is, we will say a function f, right. So, we will say a function f is convex if when I say is convex, is a convex function, that is what I mean, if the epigraph of f is a convex set. Is called a convex function, right. So, this is a definition. So, given a function, I compute the epigraph of the function, and if I see that the epigraph is a convex set, then I will call the function a convex function, right. So, this function, again let me make this clear, this is Rd to R, right. So, the epigraph is in Rd plus 1. So, this is a convex function, right. So, this is this, you can of course, I need to specify what the f is, but pictorially at least it looks like this is a convex function. Again, pictorially speaking, what might not be a convex function? Well, a function which maybe looks like this, right. So, maybe it gets extended after that, right. So, now is this a convex function? Well, not really, because now the epigraph is going to be all these points. Now, so the set is, the epigraph set is not a convex set, because now I can take 2 points in the epigraph set associated with f, and because the line joining those 2 points, as now you have to think of this as a in R2, right. So, this is R2, this line joining this in R2, the line segment does not entirely sit inside the epigraph of f in this particular case, and so this is not a convex set, right. And so this is not a convex function also, right. So, this is one definition of convex functions, but there are other definitions as well, and that is what we will see next. Okay, so here is a very interesting and relevant alternate definition of convex functions. Alternate definition, let us call this definition 2, right. So, we already had definition 1, and again this can be easily pictorially visualized. You have a function like this, and you want to ask if this is a convex function. Well, let me take 2 points x1 and x2 and see where their function evaluations are, right. So, this is f of x1, and this is excuse me, this is f of x2. Now, if I take a point between x1 and x2, right. So, and you know how to get points between x1 and x2, it is just lambda times x1 plus 1 minus lambda times x2 for some lambda. Let us say I pick it for some lambda here, right. So, this is lambda x1 plus 1 minus lambda x2, let us call this x3 perhaps. Now, I see how is the function's value at x3, right. So, now if I look at this point which is lambda, which is f of x1, and this point which is f of x2. Now, if I use the same combination, but not for the data point, but for the function's value, right. So, which means that if I look at lambda times f of x1 plus 1 minus lambda times f of x2, right. So, if I look at that value, and now as if I think of that as a function of lambda, now how is that going to look like? Well, that will be simply, you can think of it as when lambda is 0, it is going to be well, lambda is 1, it is going to be f of x1, and if lambda is 0, it is going to be f of x2, and in between it is going to kind of linearly interpolate between these two values, right. So, and that would be something like this, right. So, now for a new x3, if I look at the corresponding value on this line segment that interpolates between, you know, f of x1 and f of x2, now that value would actually be higher than the value of f of x3 itself, right. So, the function's evaluation at x3, which is this value, right. So, this is maybe f of x3 is less than in this case lambda times f of x1 plus 1 minus lambda times f of x2, right. So, now if f is a convex function, then it necessarily has to be this case, right, which gives us our alternate definition. A function, again for simplicity, let us think of this as Rd to R is convex if and only if for all x1, x2 in Rd and all lambda in 0, 1, if it happens to be the case that f of lambda x1 plus 1 minus lambda x2, which is the function's evaluation at this point, the x3 in this case we called it x3, is less than or equal to lambda times f of x1 plus 1 minus lambda times f of x2, right. So, this is another way to define convex functions, and one can show that this is exactly equivalent to our previous definition as well. Now, just to confirm that you might have a function of this form which is like this, right. So, now which means that if I take 2 points and then linearly interpolate, maybe I look at this point which is x1, maybe this point, this is x1, this is x2, and maybe this is x3, right. So, the function's value at x3 is actually higher than the function's value of the interpolation of x1 and x2, lambda of f of x1 and f of x2, right. So, this is lambda f of x1 plus 1 minus lambda f of x2, whereas this is f of lambda x1 plus 1 minus lambda x2. And in this case, it happens that this is higher than the linear quantity, and so this cannot be a convex function, right. So, which implies not convex, right. So, in some cases finding the epigraph and trying to prove the epigraph is a convex set might be a little harder, whereas you can probably apply this definition and exhibit certain points directly to show that a function is not convex, or you can show that for general x1 and x2, if you can argue that this holds, then well, that is another way to say that the function is also convex. What we will do next is look at another alternate definition of convexity, which is again very useful. Okay, so this is the third definition of convexity. So, this is definition 3, and for this definition we are going to assume that our function is differentiable, right. So, is differentiable, which means that the gradient of the function exists at every point, right. So, now assume f is differentiable. Now, we want to argue, what can we argue? We want to say that f is convex if and only if the following holds, right. So, you take any point y and you compare it with f of x plus y minus x transpose del f of x. Now, it will be the case that f of y would be greater than or equal to this. So, this needs some explanation. but this is the definition. What are we saying here? We are saying here that we take a function, let us again look at a simple function, right. So, let us say this is the function, and maybe this is my x. Now, I want to compute, of course, this is f of x, that is fine. I want to compute f of y at some other point. Now, let us say at this point, right. So, this is maybe y. Now, or y could be on the other side also, right. So, it does not, I think it is easier to look at the other side signs. Okay. So, this is actually f of y, this is f of y. Now, what does this inequality say? It says that this value f of y is actually greater than something, right. So, the left hand side is just this value, which is this quantity f of y, but what is it greater than? Well, it is greater than this quantity, which is f of x plus something, which is what? Which is, you look at the gradient of the function at f or at the point x, and then look at the y minus x transpose del f of x, which means that you are essentially thinking of this function as a linear function around this point x, right. So, which means that if you actually plot this, if you think of x as fixed and as a function of y, if you plot this, think of this as a function, then that would look like something like this. It is going to look like this, and now if you ask what is the value at a particular y that we have, that value is going to be here, right. So, now what are we saying? We are saying that this quantity here, right. So, this is f of x plus y minus x transpose del f of x. Of course, there is no transpose or anything in one dimension, but then this is a general thing, right. So, your x could be in RD in general, which means that instead of a line, you are going to think of this as like a hyperplane that supports the function at this particular point. That is what it means, right. So, now essentially in words, what is this saying? Well, the function's value is always greater than the linear approximation that you can get at any point, right. So, this is nothing specific with x. I can take some other point. Now, if I ask the same question, if this was my x dash, then the function, the linear approximation of the function at x dash is going to look something like this, right. So, now this would be well, for as a function of y, this is going to be f of x dash plus y minus x transpose del f of x dash, y minus x dash transpose del f of x dash, and so on, right. So, this now again you can see that the red line lower bounds the function itself, the blue line also lower bounds the function, and no matter which point you take, if you take the function, the linear approximation of the function at that point, it is going to lower bound the function, right. So, and if this happens for every point, then the function is convex, right. So, this is another alternative definition, and which will be very useful maybe in proving certain things about certain machine learning problems also. Okay. So, what does this essentially, what does this essentially mean, right? So, if you remember from our gradient descent type of a discussion, we argued that, you know, if you have a function which is f of x plus epsilon d, we said that our Taylor series would say that this is something like f of x plus epsilon times d transpose del f of x plus some higher order terms, right. So, and now I am going to think of, let us say, if I ignore the higher order terms, right. So, higher order terms, and I am trying to approximate this function using only the linear terms, then this approximate function is going to look like f of x plus epsilon d transpose del f of x, right. So, it is just this part, I have removed the other part. Now, what is this telling us? So, this is what this was a notation we used in gradient descent algorithms description, Now imagine y is just x plus epsilon d, right. So in this case just substitute y as x plus epsilon d, which means that if you want f of y, right, so f of y would be f of x plus, well, what would be epsilon d be? Epsilon d, because y is x plus epsilon d would simply be y minus x. Now transpose del f of x plus higher order terms, and now we are saying we are ignoring the higher order terms and then only thinking of this as a linear function at that point x. Now this is no longer going to be equal to, because you have removed the higher order terms. In gradient descent argument we said that this is like approximately equal to this for small enough epsilon and so on, but then here something much more stronger holds, right. So what we are saying in terms of convexity is that this is always greater than or equal to, and we do not need epsilon to be small, anything of that sort, right. So the function's value will be higher than the linear approximation no matter how far you go away from that point, right. So this blue line is going to lower bound this function in the entire space of Rd, in this case it is R, right. So and if this happens for every point, then we call that function also as a convex function. So this is one other alternative way to think about convex functions. The final way that we will look at for thinking about convex functions, and this is again definition 4, and in this particular definition we are going to assume f is not just differentiable but then twice differentiable, right. We are going to think of f as twice differentiable, and we may or may not encounter this a lot, but it's nevertheless good to understand this. So think of again f as a function from Rd to R. Now I'm going to define this matrix H, which is a matrix in D cross D, where Hij is simply the partial of, think of this f as x1 to xd to R, right. So that's what this function maps. So this is going to be the partial derivative of xi and xj, right. So this is going to be a matrix of double derivatives with respect to the corresponding ij entry, and one can argue that f is convex if and only if something happens about this function H, about this matrix H. In particular, the property of H is what is called as a PSD matrix, which stands for positive semi-definite, which simply means that all eigenvalues of H are greater than or equal to 0, right. So think of this as in some sense a curvature, capturing the curvature of the function itself, and intuitively this simply means that the function always should have a positive curvature, right. So the moment it has a negative curvature, it kind of goes above and comes back below, and that is no longer a convex function, right. So only if it has a positive curvature or a non-negative curvature, we will call it as a convex function. So where is this useful? A simple example where this may be useful is as follows, right. So if you think of f of x as x squared, this simple R to R function, we already, I think, I mean it's not too hard to show that this is a convex function. I mean there are several ways you can show this. If you had to use this definition, then you would do f dash of x. Now that would be 2x. Now your H is a matrix in not Rd, it's in a matrix in Rd cross D, but then your D itself is 1, right. So it's just a one dimensional function. So and that would be because, and that value of H would simply be the f double dash of x, and your f double dash of x in this case is 2, and the equivalent notion of positive semi-definiteness but single numbers is just positivity. It just has to be positive, right. So which means that this is greater than 0, which implies that f is convex. This is another way to show that a function x square is convex, right. I mean, it's not the it's one way to show x square is convex. You can show x square is convex using all 4 definitions that we have seen, but this might be an interesting definition too. Okay, good. So we have 4 different definitions of convexity, convex functions, and all these would be useful in different situations, right? So depending on what function you want to prove as convex or not, you can use one of these definitions. It might be easier to use one of these definitions than the others.